Hello, everybody. I am going to go over the workbook material for 4.2, except for the definitions. The definitions you can do on your own. Let's talk now about the workbook. Okay, concept one. Sample surveys are examples of observational studies. Their goal is to describe the population and examine relationships between variables. Often, however, we wish to determine whether or not a cause and effect relationship exists between the explanatory and the response variable. That's almost always what we want to do, right? The problem with observational studies is that they cannot be used to establish a relationship between the explanatory and response because of confounding between the explanatory variable and one or more other variables. So when you want to show a causal relationship, a cause and effect between the explanatory and response, it is best to do an actual experiment and not an observational study, to do an experimental study. So let's talk about more what an observational study is. Often observational studies are all that people have, but it's not the best way to go about finding a cause and effect. All right, so right here, does shoe size affect spelling ability? A recent study was conducted in a suburban school district to answer the question. 30 students from grade 1 to 8 were randomly selected. Each student was administered a spelling test and had his or her feet measured. Test scores were plotted against shoe size, and a strong positive relationship was observed. Was this an observational study or an experiment? So this is an example of an observational study because a treatment was not given to any of the subjects at all. There was no treatment whatsoever, so this is an observational study. So this is an example of an observational study. A treatment was not given to the subjects. Okay, what is the explanatory and what is the response variable? What are the explanatory and response variables? So no problem, that's easy enough, right? Okay, so let's see here. So what are they trying to, the first question a lot of times give this away. So, but be more specific though than the first one. But they says, the first question says, does shoe size affect spelling ability? But what specifically was measured here? That's general right here. This is just really in general. More specifically right here, they said test scores were plotted against shoe size. Okay, so right here, the explanatory variable was shoe size. And right here, we're talking about a spelling test, right? So the response variable was the spelling test score. Okay. So that is the explanatory, which remember is the independent variable, as you know it, the X. The response is your dependent variable, the Y. Okay. Suggest a possible confounding variable in the setting. Explain how it may confound the results. So I'll be honest, when I first saw this, the first thing I noticed for confounding was the fact that right here, that it was conducted in a suburban school district right here. Now, but the issue there is that's the population. So they could say, like in the conclusion, that, if there was an actual, if it was an experiment, you could say, all right, this is only for students like those in the study of suburban school districts. So right here's more specifically right here, though, what you want to do, instead of looking at the actual population that you're measuring, look more specifically about what's happening right here. So they got 30 students from grades 1 to grades 8. So then I thought more specifically, okay, well, students in grade 8 for one are going to have bigger feet. And the older students will have bigger feet. The older students also will be better spellers in general, of course, because they've had, spelling and, as a subject in the other earlier grades. They're in general just better spellers. So that means that the confounding variable here would just be age, all right? So I'll just go ahead and say a possible confounding variable. In this setting is the age of the students. And just to back that up, we'll go ahead and say the older students will generally have bigger feet and, of course, they will be better spellers. Of course, we're talking generally right here. All right, they will generally have bigger feet and will be better spellers right here. This will, and so of course this is going to affect the actual results. Because the younger students will generally not perform as well on the test and have smaller feet. Okay, something about like that. I don't know if that last sentence is even really necessary now that I see it. I think actually just up until this point right here should have been fine, right? I was just backing it up a little more, just being careful, but I think that was I was just being a little overly careful. I think actually, yeah, up until this point right there should be okay. Okay. All right, so let's move on. All right, let's go to concept 2. If we wish to establish cause and effect, which almost all the time is the point, right? We must conduct an experiment in which treatments are imposed on experimental units and other potential influences on the response variable are controlled as much as possible. All right, a lot of information here. So right here, what we want to do is we want to conduct an experiment. We want to have treatments that are imposed on the experimental units, otherwise known as subjects, right? And other potential influences on the response variable, such as, and that's confounding variables, are controlled as much as possible. The basic idea behind an experiment is that we obtain experimental units, apply treatments, and measure the results. When conducted properly, experiments can provide good evidence of causation. Proper experimental design incorporates 3 principles. First, so we have 3 principles here for experimental design, right? First of all, we must control for the influences of variables that might affect the responses. We must control those confounding variables. Okay, we want to ensure that any changes are due to the treatment alone as much as we can. Secondly, we must randomly assign experimental units to treatments. So right here, yeah, like we said in class, not only do we have to go and do random assignment just for the sampling, but then once we actually have that sample, we must randomly assign experimental units to treatments. This helps ensure equivalent groups. This helps ensure equivalent groups of units. Random assignment helps ensure that the effects of variables will be felt equally by all groups in the experiment, so that the only systematic difference between groups are the treatments themselves. Yes, that's good. I think that, guys, that this sentence right here is a little unnecessary right here and a little bit confusing, so just start right here. So we'll just go right here. Continuing on, random assignment helps ensure that the effects of variables will be felt equally by all groups in the experiment, so that the only systematic differences between the groups are the treatments themselves. Finally, the third thing, replication is necessary. Remember, that means just to increase the n value, increase the amount of subjects. To ensure both experimental units are in each group to convince us the differences in the effects of the treatment can be separated from chance difference between the groups. If a difference between groups is observed that is too large to have occurred by chance alone, we say it is statistically significant. We'll learn more about that later. We will learn how to establish statistical significance in a later chapter. For now, focus on how to assign a quality experiment. Okay, let's do it. Mr. Tyson teaches statistics to 150 students. He is interested in knowing whether or not listening to classical music while studying results in higher test scores than listening to no music at all. Okay, so he wants to compare no music at all to students listening to classical music, and this is, of course, while studying. No problem. He wishes to design an experiment to answer the question. Okay, no problem. What are the experimental units right here? Explanatory variable, treatments, and response. Okay, so no problem. Well, they should have actually asked this question later on when they said to describe a study right here. But anyway, let's answer it as well as we can. We know that the experimental units will be the 150 students. 150 statistic students. That's actually important that they're statistic students because, of course, maybe students that are not taking statistics would respond differently to this. Okay. All right, next right here, we're going to say the explanatory variable. So they're trying to see if classical music or no music makes a change right here to higher to their test score. So right here, so the explanatory variable is whether or not students listening to classical music or no music. So actually, I'll just say whether students are listening to classical music or no music while studying. Okay, there we go. And then the response variable is, of course, right there, test scores, right? So this is going to be the response variable. This is going to be the students' test scores. Okay, so that was number one. Next, let's do it. What other potential variables could confound the results in this situation? How could they affect the results? How could we avoid their effects? Okay, this one was a little tricky. Again, right here, the first thing I personally thought of, I'll be honest, is, oh, well, he's only giving these to his statistics students. But That's different. That's a population sampling thing. All right. So there, basically, if we concluded some cause and effect here, we could easily fix. We could just say, all right, this just applies to statistics students, perhaps maybe just statistics students in this teacher's school, something like that. So that's actually, we wanted to say, just forgetting that it's only statistics students, what other variables could be confounded here? Well, let's see. So right here, we're talking about classical music, right? I don't know, but I'm assuming that students that are, take music, or specifically, any student that takes music or is in band might be more familiar with classical music than students that are not. So one confounding variable right here one possible confounding variable is whether students are familiar with classical music. And how would this affect it? Well, it could cause a different response. If I hear a song that I know and I'm trying to study, I might be more distracted or something like that. So this could affect performance, while a student is trying to study. Performance, or even just, or just, you could even just say, this could affect another way, you could just say retention, right? Okay, so something like that, I think, there, it's possible maybe you could think of a different confounding variable, but that's definitely for sure one. Okay, describe a completely randomized design for Mr. Tyson's experiment. Okay, let's see here. So, all right, what do we have here? First of all, we have 150 students. Okay, no problem. So what we're going to do is, first of all, is right here, we're going to form two groups. So how are we going to do that? Right here, we're going to form two groups by random assignment. So how are we going to do that? All right, so what we can do is we will label all 150 students, and we will use a random number generator. To find 75 different integers from 1 to 150, okay? So that is going to be right here, that when we first do that, that will be our first group. So just to remind you, we're going to have two groups. One group, it's no classical music. The other one is classical music. So this is no classical, and this is classical right here. So that will be our first group. Let's make that our no classical group. And that group will not be played classical music. Okay, and then the remaining students will be our second group. Which will be played classical music. All right, so right here, now right here, we have to go and make sure that every other type of, you know, a variable is just is the same right here. The only difference is that, so right here, so we're just going to say Mr. Tyson will conduct one study session with no music for the first group, another study session with classical music for the second group, keeping everything else constant. And then, of course, right here, we're just going to give both groups a test with the same test. Both groups will be given the same test, and we will compare the results. Sorry. All right, my answer might have been a little wordy right here. We will form two groups by random assignment. You do have to say that. We'll label all 150 students, use a random number generator to find 75 different answers from 1 to 150. You do need to say that. This will be our first group. You could have left out which will be played classical music. You can say that's going to be our first group. The remaining students will be our second group, because know what I already said right here. I repeated myself. I said, Mr. Tyson will conduct one study session with no music for the first group, another study session with classical music for the second group. So that's okay. We already said the first group and second group. So I guess I didn't have to go and mention, I just basically repeated myself right there. And then right here, we're keeping all the variables constant. Both groups will be given the same test. We will compare the results. All right, something about like that. All right, I know it's a little bit of annoying comparing this. So guys, all right, so I will come back with the third one. So this video is already long enough.